Hi everyone, welcome back. Today let's look at the work of Robert Downey Jr. in chemistry. Not exactly Iron Man, but someone who looks like him. Someone whose work I'm sure you're familiar with, but have forgotten the person himself. At least I did, and I hope I'm not the only one. He's the first person to win the Nobel Prize in chemistry, one of the founders of physical chemistry, Jacobus Van't Hoff. Jacob was born on 30th August 1852 in Rotterdam, the Netherlands. He was the third out of seven children and inherited his father's name, which I'm assuming was pretty common back in those days. His parents wanted him to take medicine, as the father himself was a physician. Because of this, Jacobus was interested in science from an early age, very curious, and frequently visited botanical gardens. He was also good at mathematics, loved poetry, and philosophy. Lord Byron was one of his favorites. One source says that his interest in chemistry probably stemmed from observing chemical mixtures and medicine in his father's apothecary. You can see he was not limited in his interest to explore. So, against his father's wishes, he studied chemistry at Delft University of Technology from September 1869 to 1871. He received a technology diploma in chemistry after passing all the exams of a 3 year course within 2 years. However, after working at a sugar factory as a chemical technologist, he found the work boring. So he decided to pursue further education and started studying mathematics for a year at University of Leiden. From 1872 to 1873, he went to Bonn to work with August Kekule, which is where he must have heard about the work in the space of arrangement of atoms, such as that of Alexander Butlerov. He then went to Paris to work with Adolphe Woods, where he met Joseph Lebel. And this is important because coincidentally, both of them would publish paper in the same domain. In 1874, Van't Hoff obtained his doctorate degree from Utrecht University by publishing a paper entitled This, which translates to Contribution to the Knowledge of Cyanoacetic Acid and Malonic Acid. Then for a year in 1876, he worked at Veterinary College in Utrecht before moving to University of Amsterdam as professor of chemistry, mineralogy, and geology. He also got married in 1878 as well. And he worked here for approximately 18 years till 1896, after which he would join as an honorary professor at University of Berlin. Now, there are three areas of work which we'll focus on: stereochemistry, chemical kinetics, and osmosis. He was awarded the Nobel Prize in 1901 for his work in the last two domains, chemical kinetics and osmosis. Many people say stereochemistry should have also been mentioned. So, let's start with the first one, his work in stereochemistry. Stereochemistry, basically chemistry in three dimensions. And I had so many questions about this. Like, how did we even get here? How did we identify different elements? How did we identify elements within a compound or compounds in a reaction? And theorize that the atoms are arranged in three-dimensional space. And when I was researching about this, I also learned that there was a separate evolution that also had to take place, which was in communicating these ideas using symbols and notations. So we'll try to balance both of this, the evolution of theory itself and the representation in terms of symbols and notations, because it is quite interesting. To answer some of these questions, we need to go back and first look at how chemistry was kicked off. Modern chemistry started as an upgrade to what was previously alchemy. People believed in phlogiston theory, which stated combustion could cause an increase in mass or loss of mass, as all substances contain phlogiston, which was lost in combustion or corrosion. Combustion and oxidation type of reactions would play a crucial role in earlier studies, as we'll see later in Lavoisier's work. Transition towards modern chemistry started as Robert Boyle rejected alchemy's mystical traditions. Emphasizing on empirical evidence and experimentation, Boyle documented his work meticulously. He published a book called The Skeptical Chemist in 1661, where he challenged these alchemical beliefs like that of the four classical elements air, water, earth, and fire, proposing instead that the matter was composed of atom. He thought that these ideas of alchemy were more philosophical in their approach. Moreover, his work on gases and demonstration of pressure volume relationship showcased his quantitative approach. He also differentiated compounds from mixtures and refined the concept of chemical elements. Other chemists then started isolating elements. Some were found as and called impurity in an ore, while others isolated gases such as carbon dioxide, hydrogen, which was initially called inflammable air, and oxygen, which was first discovered or isolated by Priestley, was called the dephlogisticated air. Like Albert Einstein said, if I can't picture it, I can't understand it. But before 18th century, most of the communication in chemistry was done using textual descriptions, with some using symbols that also had mystical or philosophical connotations. You can see here how the seven elements discovered during the time of alchemy were represented along with their inspirations. Even in the earlier work around 1718 that was done in chemical affinity, similar representation is seen. This table basically shows that the element at the top of the table have the ability to combine with those at the bottom. Let's quickly touch upon chemical reactions or representation of them. The earliest reaction that was written down is usually credited to Jean Bergen in 1615, which is long before, or quite some time before Robert Boyle's discovery of Boyle's law. William Cullen in 1757 used the arrow or the dart, which is what he called it, to show chemical affinity or the forces that cause a reaction. Now, we need to keep in mind that at this time, chemistry was still evolving out of alchemy. Moving on, in 1770s and 1780s, Lavoisier started conducting several of oxidation experiments in a controlled environment. One where a candle was allowed to burn inside a closed container to prove that the mass remained the same, challenging the phlogiston theory. He conducted the same experiment with elements such as burning phosphorus and sulfur. He also created oxides in a closed system, concluding that the atmosphere interacted with the metal, causing its weight to increase, and the mass gain was lost from the air. Thus, in 1789, he established the law of conservation of mass and the fact that chemical substances never disappeared and just transformed. Arrow, initially used to represent chemical affinity, after the work of Lavoisier got a different and standardized meaning, which was to show transformation that happens in a chemical reaction. This is what Lavoisier said, challenging the existing phlogiston theory, which said that the phlogiston was lost when something is burnt. About 8 days ago, I discovered that sulfur in burning, far from losing weight, on the contrary, gains it. It is the same with phosphorus. This increase of weight arises from a prodigious quantity of air that is fixed during combustion and combines with the vapors. This discovery, which I have established by experiments that I regard as decisive, has led me to think what is observed in combustion of sulfur and phosphorus may well take place in case of all substances that gain in weight by combustion and calcination. And I am persuaded that the increase in weight of metallic calces is due to the same cause. This discovery seems to me one of the most interesting that has been made since Stahl, and since it is difficult not to disclose something inadvertently in conversations with friends that could lead to the truth, I have thought it necessary to make the present deposit to the Secretary of Academy to await the time I make my experiments public. This was our step in modern chemistry. Dalton, Berzelius, Priestley, Boyle, and Lavoisier are few who are considered as the founders of modern chemistry. Berzelius' work also standardized a lot of modern chemical formula notations. Modern chemistry was established with an experimentation mindset, viewing a reaction as nothing but transformation and reaching a conclusion based on observable and measurable changes. Lavoisier and others started isolating elements or substances that could not be broken down further. Other laws, such as law of definite proportion, Avogadro's law, multiple proportion were also established, which fueled even better experimentation, led to discovery of new elements, compounds, and scientists also started to determine relative weights of different elements and compounds. These compounds and elements in a reaction were usually identified based on many factors, again, observable, such as color, smell, and this is how also many elements were named as they were discovered. Sometimes they would mistake an element for a compound back then as well. We also had some earlier versions of calorimeter that were used to measure heat. The key thing is that in modern chemistry, these results were made by studying measurable and observable effects of these phenomena, such as mass, volume, color, energy, etc. Of course, there was some theory involved about what was happening, but it had to be backed by physical observation. By mid 1800s, many compounds were discovered, and scientists were now interested in understanding what held the atoms together. Now, a bit of foundation was laid before 1800s in 1789 by William Higgins, where his work he mentioned that some sort of energy gets distributed equally across atoms when they combine. The concept crystallized in 1852 when Edward Franklin introduced the concept of combining power of atoms, which we now call valency. He suggested that each element combined with only limited number of atoms of another element or had an affinity to do so. As you can see in the following table, he measured proportions across different compound series and showed they roughly followed the same formula. Now, we need to remember there was no fully developed bond theory yet. That would happen in 1913, around 60 years later. He also showed that some element had tendency to combine with three or five other elements, citing examples like NO3, Ni3, NO5. So, following is an excerpt from his paper on a new series of organic bodies containing metal. When the formulae of inorganic chemical compounds are considered, even a superficial observer is struck with the general symmetry of their construction. The compounds of nitrogen, phosphorus, antimony, and arsenic especially exhibit the tendency of these elements to form compounds containing three or five equivalents of other elements, and it is in these proportions that their affinities are best satisfied. Thus, in the ternal group, we have NO3, NH3, Ni3, NS3, PO3, PH3, etc. And in the 5 atom group, we have NO5, NH4O, etc. Without offering any hypothesis regarding the cause of this symmetrical group of atom, it is sufficiently evident from the examples just given that such a tendency or law prevails, and that no matter what the character of uniting atom may be, the combining power of the attracting element, if I may be allowed to allowed the term is always satisfy the same number of these atoms. Let's shift gears a little bit. Do you remember how I said Berzelius standardized a lot of chemistry? Well, as part of that, in 1807, he was also the first to use the term organic chemistry to describe study of compounds derived from natural resources. As we now know, organic chemistry is all about carbon, oxygen, hydrogen, narcissism. And one of the earliest work in this area was done by Wöhler and Liebig, who discovered that the molecular fragment C14H5O2, which we now know is C7H5O, remained intact through numerous chemical transformation of oil of bitter almond. They called it the benzoyl group. Now, this basically suggested that certain group of atom could persist even as other part of the molecule were altered. And writing to the mentor, they mentioned that organic chemistry just now is enough to drive one mad. And I am in agreement with them. Researching and building upon this, Laurent Dumas and Gerald built the first modern theory of organic chemistry, the substitution theory, proposing that specific atom or group within a molecule could be substituted by other atom or groups without disrupting the core structure and nature of the molecule, meaning that the physical and chemical property after substitution only slightly differed, which was not the case when it came to inorganic compounds. This provided new ways to predict and understand chemical reaction. Here is a quick chart for comparison. So let's quickly see how substituting elements differs or affects the properties for inorganic compound and organic compound. Comparing NaH and NaCl, the replacement of hydrogen by chlorine in ionic sodium hydride dramatically changes the chemical character of the compound from strong base to very weak base. Compare that with organic compound. You see CH3CO2H and CCl3CO2H. The replacement of methyl hydrogen in acetic acid by chlorine gives a carboxylic acid that exhibits chemical and physical properties very similar to those of acetic acid. And this was the base of substitution theory when it came to organic compounds. This laid the foundation for the next theory, the type theory, proposed in 1839 by Dumas with contribution from Alexander Williamson, August Hoffman, and Gerard. Basically, this proposed four basic types, each representing a simple formula. So, a type is basically a specific group of atoms that determine characteristics of a chemical reaction. They were identified at that time based on assumption of atomic weight assumed at that time of carbon and oxygen. So, carbon was assumed 6 and oxygen was assumed 8. So, whenever you see some of these old formulas, you might see double the number of carbon and oxygen atoms in the molecular formula itself. And the type theory was a way for chemists to classify organic molecules. However, it can be said it is a bit of an earlier version of what we now call as functional groups. So let's quickly look at how it works. Here you can see the four initial types that were proposed, that were hydrogen type, hydrochloric acid type, water type, and ammonia type. The way to read this is in the hydrogen type, you can see there are two hydrogens in the bracket, and when you replace the hydrogen at the top with C2H3, you get methane. Now remember, this was assuming carbon weight equal to 6 instead of 12, which is why they're counting two times the number of carbon. Similarly, when you replace it with C4H5, you get ethane. When you move down the ladder for the hydrochloric acid type in HCl, when you replace the hydrogen with C2H3, you get methyl chloride. The marsh gas type that you see at the bottom of the chart was something that was added later on by Kekule. There's one obvious problem though. You can have the same molecular formula and belong to two different types. For example, the formula C2H6 can belong to both the hydrogen type and the marsh gas type. And due to this limitation of type theory, structure of the compound had become an intriguing question. Which brings us to our next theory, the structure theory. A quick recap: we've established so far some basic laws of chemistry, realized that some elements combine with 3 to 5 elements on regular basis, such as nitrogen. We have identified behavior of organic compounds and made attempts to group that behavior. So, keeping that in mind, let's move forward. All right. So structure theory is how we all basically study organic chemistry in 12th standard. It is multitude of ideas that dealt with structure of organic compounds, their representation, and how those structures affected the chemical or physical properties. And a lot of people contribute to different aspects of this theory. Two important things were established about the carbon atom in 1858 by Couper and Kekule. Number one is the tetravalent nature of carbon atom and the fact that it combined with four other elements, just like nitrogen had a trivalent nature. And number two, that a carbon can combine with itself to form long chains. This would become extremely important discovery, and Cooper's linguistic background must have certainly helped in developing symbolic representation of compound, and Kekule's architectural background must have certainly helped in visualization, as we know he later on would discover structure of benzene. Even though Cooper had completed the paper before, Kekule published it 1 month before Cooper, and in some earlier texts, Kekule is given the sole credit. But now both of them are recognized as someone who established the tetravalent nature of carbon atom. So both established the tetravalent and catenation behavior of carbon atom, which are the basis of structure theory. So what was different between Kekule and Cooper's work? Kekule's theory was kind of an extension of his work on the type theory, and also one of the reason it was easily accepted, its conservative nature. You can see here how the representation of hydrolysis and a monolysis reaction still shows compounds at different types during a reaction. Whereas Cooper advocated for a complete overhaul, get rid of it all, start from scratch, give it a new structure. He utilized dashed lines to illustrate interconnection between atoms, and this illustration of Cooper was later refined by Brown in 1861, which represented each atom as a letter inside a circle connected to its neighbor with a solid line. With slight modification, we still use this today. You can see here the difference in structural formula of Kekule versus Cooper. In succinamic acid represented by Kekule, you cannot see the backbone of the molecule and is drawn as mixed type. In Cooper's tartaric representation, on the other hand, the backbone of the molecule is clearly shown and closely resembles the modern representation. Because Cooper's theory went a little more further, Butlerov, who is another prominent figure, disagreed more with Cooper's theory. Even though he did believe both theories were incomplete, both Kekule's and Cooper's, because they focused more on the idea of carbon bonding and less on the actual significance of how the structure itself is determining the chemical properties. He believed that there has to be something observable to give reasoning to a structural design. And this stems from the idea of how modern chemistry was founded. He saw theories as a series of behavior from which we can induce laws, and saw no reason to deviate from the type theory. He was concerned that Kekule and Cooper recognized the importance of atomic connection, but they did not fully develop the idea that specific arrangement of these bonds was what truly determined the property of the compounds. So he was concerned that while Kekule and Cooper recognized the importance of atomic connections, they did not fully develop the idea that the specific arrangement of these bonds was what truly determined the properties of a compound. He would move past these concerns, as later on Butlerov would advocate structure theory and become one of the biggest proponents of it. He in fact coined the term chemical or molecular structure in his paper in 1861. This is the paper in which he puts forward his version of structure theory, which was more closer to Cooper and in line with what he believed, stating only one rational formula is possible for each compound, and when the general law governing the dependence of chemical property on chemical structure have been derived, this formula will represent all these properties. Hence, basically set a limitation that each compound be represented by a single structure and that a structure represents a single compound. He pointed out that chemical structure was different from physical structure, not implying anything about the location of the atoms or topography of molecules or arrangement of the atom in space, and it was more about the relation between the atoms. Kind of restating Cooper's theory, but in clearer terms, he says the well known rule that says that the nature of compound molecule depends on the nature, the quantity, and the arrangement of elementary constituents can for the present be changed as follows. The chemical nature of a compound molecule depends on the nature and the quantity of its elementary constituents and on its chemical structure, hence coining the term chemical structure. He did comment and credit Couper in a lecture in 1861, saying, I'm even obliged to remark that the theory and formulas of Couper, whose two absolute and exclusive conclusions are disputed at the time, contained similar thinking. It was, however, neither clearly enough perceived nor expressed. His theory also included initial groundwork on isomers that stated it is possible to predict existence of new isomers of known compounds by preparing these compounds themselves. He produced isomers of amyl alcohol, tert butyl alcohol, butyric acid, and butenes. These were structural isomers which could be basically position of atoms in a chain, position of double bonds. He proved that these were isomers by showing that even though molecular formulas were same, these compounds were different by behavior, such as rate of reaction for isomeric alcohol was different. Or for acids, it would be that when reacting with the same compound, they would give different outcomes. Or they could just be different physical properties such as boiling point or solubility that differ between isomers. Here you can see how Butlerov represented some of the isomeric butenes. The apostrophe basically represents unsaturation, and basically figure 1, 1a, 1b are isomers is what he's showing over here. Finally, let's come back to the main person of this video, Van't Hoff. Van't Hoff had written a 12-page pamphlet contributing to the realm of structure theory. Van't Hoff proposed arrangement of atoms in three dimensions by putting forward the tetrahedral structure of carbon atom, where a central atom is located with four substituents that are located at corners of a tetrahedron. Now, Lebel is also credited with the discovery of tetrahedral structure, and Van't Hoff had acknowledged it. The tetrahedral representation is considered to be a significant breakthrough to answer many questions, as well as being the starting point of stereochemistry.
There were two key highlights of Van't Hoff's paper. First, the tetrahedral structure of carbon atom, and second, how the optical properties were related to this arrangement around the carbon atom. Let's start with the first one. Assume we have a molecule with carbon and four different elements attached to it: R1, R2, R3, and R4. I wanted to try to draw all possible isomers or permutations for its molecular structure in two dimensions. You will find that there are three permutations possible. My question is, what would happen if we had represented this instead in three-dimensional space? Would the permutations increase or would they decrease? Now, before we answer that question, let's quickly set baselines for permutations with different molecular formulas. He mentions if a formula follows the structure CH3R1 or CHR1 times 3, they have one permutation possible. Similarly, if it follows the formula CH2R1 times 2, CH2R1R2, or CHR1 times 2R2, then there are two possible permutations. And like we saw before, if all four elements or molecules attached to carbon are different, then we have three possible permutations in case of CHR1, R2, R3, R4. Contrary to what I thought, the permutation will actually reduce in three dimensions. Let's go for the most extreme case where all four elements are different. And this is what he writes in his paper. If one imagines the head in R1 in the line R1, R3 looking at the line R2, R4, then the R2 may be on the right as shown in figure 7 or on the left as shown in figure 8 of the observer. To make it simpler to visualize, for image 7, when you see R1's point of view, the R2 is on the right of it. Basically, it is inside this plane or screen you're watching this video on. Now, even in image 8, R2 seems to be on the inside of the plane, the way it's drawn. However, R4 this time is at the bottom. So try to rotate this image upward such that R4 is brought to the top. You will see R2 then points outside the plane or outside the screen, hence it is on the left of R1. It concludes that in the case of four affinities of carbon atom, if four of them are mutually different univalent groups, two and only two different tetrahedral can be obtained, which are mirror images of each other but can never be conceived as covering each other. That is, one has to deal with two isomeric structural formulas in space. This is how he made the case that atoms are arranged in three dimensions or tetrahedral manner, citing examples of isobutyl alcohol, lactic acid, tartaric acid, saying that we don't know permutation of these compounds to be more than two, which even Butlerov had confirmed in his experiments. Moving on to the second part, he associates the ability to rotate plane polarized light to this asymmetry of carbon atom. He mentions that every compound rotating plane polarized light contains an asymmetric carbon atom and cites a couple of examples of compounds that follow this rule, such as aspartic acid, malic acid, glutaric acid, tartaric acid, etc. However, in the paper, he never mentioned that the discovery of some compounds to rotate polarized light in two different directions was because of these mirror isomers. But it was later on when the paper became popular, scientists made the connection themselves, building on top of the work of Pasteur and referencing the work of Lebel. It was Pasteur who identified the difference in shape of crystal that caused the light to rotate in two different directions for tartates. He separated crystals by looking at them under a microscope and identified that they were non-superimposable mirror images. He said this happened due to internal asymmetric arrangement of molecules, but he never gave a molecular model at that time. Van't Hoff, being the gentleman he was, also recognized contributions of Lebel. Later on said, "On the whole, Lebel's paper and mine are in accord. Still, the conceptions are not quite the same. Historically, the difference lies in this, that Lebel's starting point was the researches of Pasteur, mine those of Kekule. My conception is a continuation of Kekule's law of quadrivalency of carbon, with the added hypothesis that the four valency are directed towards the corner of a tetrahedron, at the center of which is the carbon atom. All of the compounds of carbon which in solution rotate the plane polarized light possess an asymmetric carbon atom. This was the 12-page pamphlet initially published in 1874, which he distributed at his own cost. This shows his dedication to his work at a young age of 22. He later published an enlarged version in 1875, a year later, in French, which was a much more prominent language for research back then, where he addressed a lot of criticism that he had received. One of which was that many forms of tartaric and malic acid were inactive to plane polarized light, even though they had an asymmetric carbon. This is where he wrote the formula for maximum number of stereoisomers possible being equal to 2 raised to n, where n is equal to the number of asymmetric carbon. And he said that if we have a general formula like CR1R2R3 dash CR1R2R3 with two asymmetric carbon, such as that of tartaric acid, each asymmetric carbon having the same substituents, then two of the mirror images would be identical, hence optically inactive. Van't Hoff also prepared tetrahedral cardboard models and distributed amongst various scientists to simplify communication. His work became even more widespread only after a German translation was published in 1877. Johannes Willison has recommended his work quite a lot and also wrote preface to the second edition in 1894 of the enlarged version of Van't Hoff's work. It could be that his work didn't get recognition because he was young at the time and the atomic theory wasn't developed much. It was only after his work in osmotic pressure and Einstein's paper on Brownian motion that his work got his due recognition. Eventual impact was proliferation of the idea to think about chemistry in three-dimensional space, establishing chemistry in space. By giving a geometric reason behind the number of isomers that can exist for an asymmetric carbon atom, and also associating this asymmetry of carbon to show ability to rotate plane polarized light, which solidified the structure theory even more by saying the three-dimensional structure plays an important role in explaining these physical differences. All right, so that's it for this video. We'll have to make part two for the other two topics that contributed towards his Nobel Prize. Until then, take care and namaskar.